Hey everybody, very happy to be here today to give you a little whirlwind tour of ion source fundamentals for liquid chromatography, mass spec, and gas chromatography mass spectrometry. My name is Kevin Shug. I'm a professor at the University of Texas at Arlington, and I'm going to take you through a few different aspects of different ionization techniques. I'll give you first a little bit of a historical perspective and talk about, a little bit general aspects of ionization and ion sources, and then we'll get into the meat of the presentation with the various different ways that you can create ions for GCMS and LCMS. I always like when I'm teaching these things to go back into the historical perspective, the history a little bit, just to kind of remind us that, these are techniques that have developed in the not too distant past. Okay, yeah, sure. At the end of the 1900s, we were discovering the electron and then getting into the discovery of the isotopes. But it wasn't until the 50s that we had, the first quadrupole and ion trap conceived, and didn't have the first GCMS until 1956 when McLafferty and Gulke did their work at Dow. And then you really see the development of GCMS kind of take off, but it still is 20 years before there's a commercial GCMS made available by Finnegan. The first commercial quadrupole wasn't until the late 60s. And all along through here, there's development of new ionization sources and improvements of instruments and whatnot. And LCMS, its history is even more limited. And we'll talk about why as we go through the talk, but there's a lot of time searching for appropriate ways to couple liquid chromatography to mass spectrometry, and really it wasn't until the 90s that you really started to see commercially viable systems and being adapted and developed. And of course now these things are pretty commonplace in our laboratories, but they don't have that long of a history. At least I like to think so, because I was doing my graduate work around the turn of the century. So getting into some of the different, what we want to do here is we want to convert molecules into gas phase ions in a high vacuum environment. And to do that, we have to apply enough energy to get these molecules over an ionization potential, that minimum energy that they require to become ionized. So we apply energy, and we can do that in many different ways. We can really broadly characterize some of these ionization sources as hard ionization sources or soft ionization sources. And as you might surmise, when we have hard ionization, we're putting in a lot of energy into the molecule, and we generate ions, but we often also generate quite a bit of fragmentation of those different ions. And so this provides maybe potential for creating like a puzzle pieces that you can put back together for qualitative analysis. Or you have techniques that are softer that, just put in a little bit of energy, enough to create what we call the molecular ion. So an intact molecule that has been ionized. And those generally don't have a lot of fragmentation. So you have to follow on with some tandem mass spec type of experiments if you want to interrogate them further. And we'll also talk about even and odd electron ions a bit. And just to kind of familiarize you with that a little bit, you can think of an even electron ion as one where all of the electrons are paired. That would be like a protonated or deprotonated molecule, versus an odd electron ion would be something like a radical cation, where we've just knocked one electron off, knocked off one negative charge, so we've got a residual positive charge, and those are formed by some other different ionization techniques. So just very quickly, just kind of look at how the ways that we create ions, how we apply energy. This is just a listing of some common, some more common than others, some more used than others, and I'm highlighting the ones in blue that we'll talk about specifically. But we can use electrons or reagent ions or high potential electrodes, laser beams, anything that we can do to impart energy onto the molecule in order to get it over that ionization potential. And if we want to do this, we want to do it well. We're trying to make sensitive analytical measurements, and so as you all are aware, we can do that quite well. But we want to be able to create a lot of signal, a lot of ion current, and those characteristics are achieved well with some reasonable ion flux for a wide variety of different ion sources. We want to be able to very efficiently convert these molecules into ions, and that can vary a lot for different ion sources, but even 0.1% conversion to ions creates a lot of ions to work with. We'd like to be able to see positive and negative ions, and we can do that. We'd like to be able to look at higher molecular weight compounds, and we can do that. It's just a matter of choosing the appropriate ion source for the molecule that you're interested in studying. And we can do this for all different sample types. There's mass spec applied to liquid, solid, and gaseous samples. Once we've created these ions, the instrumentation is such that we can really precisely control any additional energy that we put into the ions to create fragments so that we can perform, let's say, some more qualitative assessments. So GCMS, talk about first. Obviously, here we're dealing with volatile and semi-volatile organic compounds typically, those that are thermally stable. They have to be able to make it through the GC. And with the techniques that we have, we're generally able to detect almost anything that comes through there. Electron ionization is the most common ionization technique that's used with GCMS, and this is a hard ionization that creates odd electron ions. So you create a lot of fragmentation, but what's really great about this technique is that if you're trying to figure out what you're looking at in your mass spectrum, you can pull up a library of mass spectra and match it to what you've measured. And so that obviously aids qualitative analysis quite a bit. The other techniques I'm going to talk about don't have that capability. Even people try to work and develop maybe their own libraries, but electron ionization is the one that has a really widely available library for qualitative analysis. Second to electron ionization is chemical ionization. This is a bit softer. It can create even and odd electron ions. As I said, there's no library. The main advantage here is that whereas when we blow the thing apart with electron ionization, with chemical ionization, we often observe this molecular ion, so that we see a signal at the mass to charge ratio that roughly corresponds to the molecular weight of our molecule. And that can be advantageous for quantitative analysis. If we can keep all of our signal in one ion form, and we're going to do something like a multiple reaction monitoring experiment for quantitative analysis after that, we'll have the best sensitivity using a ionization source that puts most of the population of our ions into one signal, versus in electron ionization, we create a lot of different ions. You can still do MS following that, but it's just some, again, considerations for what you're trying to achieve. And one tip I always like to throw out there, because it was something that I was told when I was learning, these mass specs are complicated, but, even 90% of the issues that are occurring, errors, things that you've got to troubleshoot and work with, those are usually errors that are occurring in the GC inlet. So if you're having problems with your GCMS, don't overlook the what might be happening just in the inlet, even before the GC separation. We might, be tempted to just go and consider that it's, a complicated mass spec that's acting up, but it could be just a loose fitting or some kind of a leak there in the inlet that's causing our issues. Okay, so let's get into these different sources. Electron ionization source, here we have our effluent coming from the GC column. This goes into a low pressure environment ahead of the mass analyzer. And the molecules encounter this essentially ionization current from a cascade of electrons. Those electrons come through and at 70 electron volts impart a lot of energy into the molecules to create ions that once these ions are formed, will feel the repeller electrode and be sent forward into the mass spectrometer for analysis. And the 70 electron volts is pretty consistent across all of the different types of GCMS electron ionization systems that you can purchase. So the reason why is this. So this is a plot of the logarithm of ion current, how many ions are generated on the y-axis versus the input electron energy. And I have those little arrows on the curve because that curve can shift back and forth depending on what molecule you're studying. But in general, if we apply a little bit of energy, we can reach this ionization potential and start to generate some ions. And when we do that with pretty low energies, we're going to just principally create molecular ions. And as that energy now is ramped up to a little bit higher energy, the production of fragment ions becomes important to this ion current that we're measuring. And ultimately, but again, the degree of this fragment ions is going to be very much dependent on the molecule if we were just sitting at this particular energy. What we end up doing for electron ionization is working in this plateau region where principally fragment ions are formed. And in fact, the standard EI ion source energy is way out here at 70 electron volts. And that's really just to ensure that all molecules in all different instruments can be reproducibly fragmented into a whole series of diagnostic fragment ions that, again, we can match to a library. Now, this is obviously a very well-established technique, and we have these spectral libraries. We don't have a lot of issues with ion suppression and matrix effects like we will talk about in some of the other sources. But if you are trying to find the molecular weight, see what the molecular weight of something you made is, this could be problematic because you might not see the molecular ion. You might just see fragments of that. So for true unknowns, you might be limited in the information you get with a standard electron ionization experiment. There is developing trends to develop more of what are considered cold EI sources, where you can tune this electron energy to be able to see both fragmentation that can match library spectra and also the molecular ion. So that's a more recent development in electron ionization. And then there are people who are very actively and successfully starting to use this more for combining even LC with MS. Again, the principal motivation for doing that is to be able to now have some mass spectral libraries for LCMS type experiments. Moving on to chemical ionization, in order to achieve this second most common ionization source for GCMS, what we're going to do is we're going to take the electron ionization source and we're going to flood it with a reagent gas. The most commonly used reagent gas is methane, but also ammonia, isobutane are not uncommon. So when this methane encounters the electron ionization, basically it creates a whole series of reagent ions. And these reagent ions are then the ones that will interact with the effluent, the molecules in the effluent from the GC, and then they can impart ionization through a variety of different ion molecule reactions. Here I'm just showing an example where you could have CH5 plus, do some proton transfer to protonate a molecule, or you could have, C2H5 plus, initiate some type of a hydride transfer where it takes a proton away, takes a hydride away, leaving a positively charged ion behind. And there's a lot more to these mechanisms of that, and obviously you can have some differences when you have different reagent gases. But in general, the mechanism is that we have a reagent ion that is transferring charge or initiating a charge transfer reaction with the molecule. And this is a much softer ionization, and as a result, as I said before, the base peak is often the molecular ion formed. Sometimes it would be, for particular analyses, we try to gain some selectivity. And if we have electronegative compounds, things like halogenated compounds or nitrosylated compounds, these compounds are electronegative, and they can be very selectively detected using negative chemical ionization. So these electronegative compounds have the ability to capture an electron and create a negative ion. So what we do is we'll take this EI source, we flood it with a reagent gas. Still, methane is very commonly used, and when methane is if we reduce the polarities in the ion source and flood with methane, then basically we create a system where molecules that can capture an electron and create negative ions will, and then they can do so very selectively relative to, let's say, maybe a high background of other compounds in the sample. So this is and it's also done very sensitively. So it's a very effective process for detecting these environmental contaminants. mainly obviously for quantitative analysis. It's not like we have a library, but it is a soft ionization technique. And you can see some significant variability in operation between different instruments, but it's certainly a useful tool in the toolbox. We just take a look, a little bit of I don't have a lot of time to show a lot of examples, but this is a good summary kind of comparison that I pulled from the literature. The top three spectra are of a 18-0 fatty acid, and then the bottom is a 25 fatty unsaturated fatty acid. And you can see in the left most columns, we've applied electron ionization to these molecules, and you see a lot of fragmentation that occurs, and maybe not a lot of the molecular ion. You see a little bit more on the top one than you do on the bottom. And then as we go to the right, the middle columns, these are the positive chemical ionization analysis of these fatty acid methyl esters. So I should mention these fatty acids have been esterified for these experiments to make them more amenable for GC. And you can see, interestingly, how this 18-0 fatty acid methyl ester now has a much higher molecular ion formed. The ones on the bottom have a little bit more molecular ion, but still see quite a bit of fragmentation. And now we switch up the strategy here. Now, fatty acids themselves don't have really a good electronegative group, but if we then derivatize with a pentafluorobenzyl group, now we have this fluorinated benzene unit attached to these molecules, and they now become quite amenable to negative chemical ionization. You can see here the principally molecular ions formed. I have to note, I believe that there's a typo in this figure from this paper, that those are negative ions on the rightmost panels and not positive ions. So it's M minus H minus rather than M minus H plus as indicated there. But still, I think an interesting comparison of the different performance you can get with these different ion sources. Okay, now switching into talk a bit about liquid chromatography mass spectrometry. As I mentioned here, this was a much later developing technique, mainly because we have so much solvent associated with these separations that we don't have vacuum pump systems that are strong enough to be able to handle all that solvent when they're converted into gas phase molecules. So we have to have some way to get rid of this solvent. And we're also trying to make gas phase ions out of thermally labile and non-volatile analytes. So that's in itself a challenge. We can't just apply heat or, like is a common constituent of GC to be able to liberate these molecules and ionize them, but we have to come up with some other ways. There have been certainly lots of ways thought about how to do this. I just grabbed this picture of a moving belt interface that was being developed by Micromass way back when. And so what they would try to do is deposit this LC effluent onto a belt that would then travel through some different vacuum seals and a dryer to remove solvent, and eventually then have that belt encounter a electron ionization, chemical ionization source, and then feed back around and be cleaned again and for the next deposition. So certainly people were thinking about a wide range of ways to be able to handle these problems. It really was the development of atmospheric pressure ionization techniques that brought LCMS into the mainstream as a very popular, capable tool. The two main techniques here are electrospray ionization and atmospheric pressure chemical ionization. And typically your instrument has both of these sources, and you can switch them out and change them within a few minutes. If we're analyzing polar and ionic molecules, then electrospray ionization is the choice, especially if we have larger peptides and proteins. John Fenn won the Nobel Prize for figuring out that you could take these very large molecules and using electrospray ionization, put multiple charges on them so that you could lower the mass to charge ratio and see them in a typical mass spectrometer. This is a soft ionization technique that creates even electron ions. So to get more information, we'll have to use tandem mass spectrometry. One aspect, though, is there is extreme variability and the ionization efficiency of different analytes, and as well, they are subject to different matrix effects. So we need to, if we're doing quantitative experiments, we have some special constraints on the types of internal standards that we use. We want to use a stable isotopically labeled variant of our analyte as an internal standard if we can. If our molecules are not so amenable to electrospray ionization, we can do atmospheric pressure chemical ionization. So think of maybe steroids, or we've done some PAHs due by APCI to more moderate polarity molecules. But we don't have any multiple charging. So we have to stay in the range of what our mass analyzer can handle. But it is a soft ionization. It can be a little bit more fragmentation than you have for ESI, and you can create both even and odd electron ions, much like from chemical ionization you could for GCMS. So electron ionization is achieved basically by pneumatically assisted electrostatic nebulization. Basically apply a high voltage at the capillary tip and have some sheath gas that's helping basically create this mist of charged droplets that will ultimately release a gas phase ion that can be sampled by the mass spectrometer. What I want to emphasize here is that most of the ionization is occurring in solution or in the droplet. So your strategy to create positive and negative ions would be mainly based on what you think those molecules can form in solutions. So acids, more likely to form negative ions, and therefore you may analyze them in negative mode. To switch the modes for electrospray ionization, we just switch the polarity of the potential we apply to the capillary. So we use a positive potential to create positive ions, negative potential to create negative ions. Those, when we apply a positive potential, we essentially suck out some of the negative ions in the solution, creating an enriched droplets of positive charge. And those positive charge wants to get away from each other. And so when they see the exit of that capillary, they will spit out into this cone jet, what's called a Taylor cone, that will ultimately release these gas phase ions. Just put it kind of more simply, capillary held at high potential, high electric field creates this mist of highly charged droplets. And then this is an atmospheric pressure regime here. So there's lots of gas molecules around to help solvent from the droplets to evaporate. So the solvent starts to evaporate. These highly charged droplets start to reduce in size. And eventually, the charge repulsion of those charges on the surface of the droplet overcome the surface tension holding the droplet together. And this is called the Rayleigh stability limit, and that will result in what's called Coulombic explosion, where basically this droplet will subdivide and give off smaller droplets, and then they go about and do the same sort of thing. They reduce in size, and they will go to another Rayleigh stability limit. And people generally believe that this is happening 3 or 4 times in the course of this, 100 milliseconds of that's where these ions or these droplets are residing in the ion source chamber. Ultimately, we have these fully dissolvated ions that we can sample by the mass spectrometer. In truth, we need to knock off a few solvent molecules along the way with the heated inlet to the mass spectrometer. I don't have a lot of time to talk about, there's lots of work being done on mechanisms associated with how different ions are formed by electrospray. I have some cited papers here for the ion evaporation model, by which it's believed that mostly small molecules are released in the gas phase, and also this charge residue model, which is believed how proteins are ionized from these highly charged droplets. And so maybe you can get a sense of then, how maybe you can get these multiply charged ions formed. So a protein could spread across multiple charged sites on the droplet surface, and then basically just survive through the whole ionization process until all of the solvent is knocked off, and then you basically get a distribution of ions with different charge states. So that mass spectrum at the bottom is a 150 kilodalton antibody that's electrosprayed, has a maximum number of charges of, let's say, not a maximum, but the most abundant charge state is 101 charges placed on that protein, which effectively now brings the mass to charge ratio down into a region where it can measure it with a simple quadruple mass spectrometer or whatever. So obviously this is really a powerful tool for bioanalysis of proteins and large macromolecules. Again, not to go into too much detail here, but a more practical model to consider is this model proposed by Chris Inke, which is the equilibrium partitioning model, and talks about this competitive process of different species in the droplet needing to migrate to this droplet surface in order to become gas phase ions. So ultimately, the ion current that we measure in our mass spectrometer is proportional to the surface concentration of species in these droplets. So the molecules have to have some surface activity, some desire to get to the surface of that droplet, and associated charge. And they got to be able to do that better than other things in that droplet as well, because there can be competition with other components in that droplet. And if you have, for example, a detergent that's very surface active, this could get to the droplet surface faster and suppress ionization of the things you're trying to detect. So again, electrospray ionization, because of this competitive ionization process, is extremely analyte and matrix dependent. We have to have these stable isotope labeled internal standards. We'd like to avoid any places where we have detergents and lipids. If you're analyzing, blood plasma or something, generally have to really be good about cleaning up the lipids, or they will greatly reduce the ionization of the things you're looking for. Similarly, we have to use volatile mobile phase additives. We want these things to evaporate, otherwise the stuff's just going to deposit in your ion source chamber. And because electrospray is quite soft, adduct ions are not uncommon. So it's not uncommon to see a sodiated or ammoniated ion. So you should be on the lookout for those. It's really very molecule dependent on what kind of ion forms they might take. Stepping now into atmospheric pressure chemical ionization. Here, what we're going to do is take our liquid and pass it through a heated chamber that's going to vaporize the sample about 450 degrees C, vaporize the solvent and the sample molecules together. And then these are passed across a corona discharge needle. So that is a very high electric field created at the sharp tip of the needle with a 5 kilovolts applied to it. And what this does is essentially, as the name implies, create some reagent ions that can then do chemical ionization. So methanol is a common component in the mobile phase for HPLC. If it's not there, then you would add it in for this chemical ionization to work well. And those basically methanol reagent ions or even water reagent ions can then transfer charge to the analytes of interest, so that they can be measured. This is at least the source for a Shimadzu instrument looks like. I was able to easily take a picture of that down in my lab. But here you have, from the right side, you have a liquid flow inlet. You'd have the nebulizing gas, and then that big ring in the middle is where this thing would plug into your ion source region. You have the block heater to create the aerosol. And then that aerosol comes out and passes across that corona discharge needle, which is held at a very high potential. Again, not as highly applied for different applications as ESI, but still very common and useful tool out there. I'll just mention here another. It's a little less common than APCI, but there are applications out there. If you take the corona discharge needle and replace it with a UV light source, like a krypton bulb or something like that, then you can now perform atmospheric pressure photoionization. So same sort of process where you're heating the effluent and creating this aerosol. But you can have different, obviously, mechanisms for ionization. You can have ions formed directly from the from the absorption of the UV light. We can also commonly put in a dopant molecule like toluene that will create dopant ions from interacting with the UV light source, and then those will then undergo charge transfer reactions to ionize your molecule of interest. And again, just to have a quick example here, this is a mixture. It's 2 fish oil fatty acids, EPA and DHA, and you can see what those are there on the bottom right. Now, I told you, ESI is soft, and you might look and say, oh, but there's a lot of fragments here on the right for these ESI measurements. Well, they're not really fragments. Actually, there are a lot of adducts. So you can see in there, M plus potassium plus sodium plus ammonium. And there's more ammonium there when you use ammonium formate in the mobile phase. So it can be quite complicated, even though you're not generating fragments. You're still distributing the ion signal across potentially a lot of different ion forms, and that may not be ideal for what you're trying to do. But you can see here these clean spectra obtained by APCI and APPI. And in this case, it looks like you get a little bit more sensitivity also for these applications with APPI. And I think that from what I've seen out there, APPI and APCI have pretty similar application bases. It's just some cases where you might have higher ionization efficiencies than others. So, I know that's a lot to chew off. You could easily have 30 minutes on each one of these and go into a lot more details, but I meant here to just give you a quick overview. So this is my summary slide, just kind of breaking down, the different sizes of molecules and polarities of molecules that you might expect to address with the different ion sources. And just a reminder there on the right of what type of ionization you have and what kind of ions are formed. But for sure, even between GCMS and LCMS, we have extremely powerful capabilities to analyze so many different things out there, and it's really just getting used to understanding the nuances of what kind of requirements you have for each one, and practically what are things you need to avoid or include in order to make them work more. So I appreciate the opportunity to give you this quick whirlwind tour, and I look forward to answering any of your questions. Thanks very much.